Okay, excellent. So a very warm welcome to all of you to our second keynote of our INREC 2021. It is my particular pleasure to introduce Thomas Dederichs, who is the head of energy policies at Empyreon. He is a very well-known figure in the energy framework in Germany. He has worked for regulatories and other industrial firms. He studied in Aachen at the RWTH in Aachen and also in London. So he has an international flair with him. And we're happy to have him here, where he wants to share his view on the system in 2050. And this is very topical and very timely. So we're looking forward to hear from Thomas Dederichs about that. Just one word on the organization. Thomas is happy to take questions in between. So if you want to raise your hand or write anything in the chat, we then will pass the question on to Thomas. But now we're looking forward to your talk. Thank you very much for being here.
Yeah, well, thank you very much for having me. This is probably not your average scientific presentation. My science days are quite some time back, and so today this might be more. I titled it with a tale of three molecules, which I will show in a minute. Regarding maybe the most important question of our time, how to realize a climate neutral energy supply by hopefully the mid-century, maybe a little sooner for some regions in the world. Maybe our region is climate neutral by 2045, but this is still a global effort basically underway. And I'm here to tell you that there is still a lot to do and that it's not too late. And I think both messages will become clear as soon as we dive into the details. Yeah, I set my presentation up in three parts. I'm going to start with obviously CO2, which I think is something most people would agree with is an important topic. I would then like to focus a little bit more on H2 because this has become very important with regards to the discussion, at least in Europe and Germany, I would say, probably globally as well. And the last one, I'm not sure if everybody's aware what that is, and I'm going to keep it a secret till the last part of the presentation. It's C3H4N. Don't look it up. It's it will ruin the surprise. So just a real quick word on who's talking to you. As already mentioned, my name is Thomas Dederichs. I've worked in the energy industry my entire career, which is not that long, but I've seen the last decade or so being involved with everything regarding grid planning and market design and questions regarding energy laws and further development. The company I'm working for right now is formerly a part of RWE. Some of you might know the liberalization in Europe and in Germany, especially, has worked quite some way now. And so the companies that were active in Germany at the beginning of the new millennium are looking very different today. And so what used to be part of RWE, the transport system, the ultra high voltage grid, ranging from the Alps almost to the North Sea, and we're now also connecting offshore grid capacity. So we will be reaching the sea very soon. And we are responsible for an area of almost 30 million people living there. Which is also generating about a third of Germany's economic output in terms of GDP. And so you can see that energy transition is a very important topic for us, because we're not just doing this for us, obviously, we're doing it for all those people living there, residential as well as industrial customers. And especially if you look at the region along the Rhine River, where most of Germany's steel production, most of Germany's chemical industry is located. We are talking daily with customers like BASF, world's largest chemical producer still, on how they want to go forward with reaching carbon neutrality and climate neutrality as a next step. We have about 11,000 kilometers of line length in Germany. We will invest approximately 25 billion euros over the next 10 years. That figure is definitely going up. At the end of the year, we will have a new national grid development plan. This figure might become substantially larger over the next few years. And we are still just, I would say, a medium-sized company. We are a little bit more than 2,000 employees. But we're still growing, and so we play a key role, I would say, with regards to the energy transition, because the TSO, at least in Germany, has a special responsibility for the holistic view on the system. So a lot of questions regarding system security, system stability lie with the TSO. We connect Europe. This is one of our, we are just a small part, obviously, of the entire transmission grid spanning from Portugal all the way to Estonia. And this is, some might say, the biggest man-made machine ever built. It spans thousands of kilometers in all directions, and it is working perfectly in sync. Yeah, the processes and the signal speed on this is fraction of the light speed. So you can imagine keeping all that system running, and it's basically been up since World War II. So the entire electricity transmission grid has never seen a complete blackout in all that time, and this is because of our people. For example, in Brauweiler near Cologne is where we as Amprion are responsible for. You see an area by the dotted line, which is our most important area that we are responsible for, but we're also coordinating frequency stability for the entire European grid area. And so, yeah, Amprion has a couple of special responsibilities with regards to system security. I promised you to start with carbon dioxide, and I'm hopefully not repeating myself, because you've obviously had a very interesting first day of talks already, and you already heard a lot about what is changing. And so I'm just putting up one slide and one graphic, and I think yeah, I would just summarize it as the science is in. There's not much discussion on the question of is there climate change happening, and is there an effect of what we as human beings are doing on that. I think that is all becoming very, very clear. However, and I find this very interesting, the question of what exactly does that mean to be responsible, and to be, the IPCC would say, very likely responsible for an anthropogenic climate change. What does that mean, and how do we mitigate those effects? And I wanted to just give you a few ideas, few thoughts of mine on that topic. I'm obviously not a climate expert, but I'm reading the IPCC reports very carefully, and I'm looking at what's happening from a political point of view. The small animation you'll see in the top right corner is the so-called carbon clock, which is put up in Berlin by the NGOs from Fridays for Future. They did a calculation, maybe you can spot it, of something like 2.7 gigatons of carbon emissions that would still be within our German budget. And this is, I think, maybe the most important scientific question regarding our shared future, regarding what has to be done, regarding on burden sharing, regarding what efforts we have to take. And it's still not really discussed, in my opinion, or at least it's very, very simplified in a political arena. In the political arena, we're usually talking about dates. We're talking about 2050 versus 2045. Sometimes we're talking about degrees Celsius, like 1.5 and 2 degrees. But it's if you look into the science, it's all becoming a question of statistics, basically, right? With climate science, we're always looking at distributions, and this is what you see in the lower right. These are the very, very new estimates from IPCC Working Group 1 regarding what is the actual amount of carbon budget still available for the entire world, obviously. And so, first of all, there's a huge variation still regarding likelihood of limiting global warming. There's still huge variations due to uncertainties. Even if you are willing to say we want to limit climate change to 1.5 degree, and we want to do this with a 67% certainty, even then you can start with 400 gigatons of budget without looking at the entire list of caveats given. There's a lot of little asterisks by that number, because there's still huge uncertainty about geological processes and even the exact determination of what amount of carbon we're actually emitting. So first of all, there's still a science question going on. On the other hand, and this is more my specialty, I would say, there's a lot of political and even ethical questions involved, because in the end, even having a global carbon budget doesn't really necessarily tell you how much each country is allowed to spend. And we're having intense discussions on this, and obviously there's some merit to simply saying let's split that budget per capita, and Germany having about 1% of global population would therefore take about 1% of the global budget. But that completely takes out of sight maybe historical responsibilities due to us having emitted for quite a long time, and other countries having basically been emission free for quite some time until recently, especially looking at China and India, for example. And just to give you an idea of what that means, I found those two graphs very interesting to look at. And on the left hand, you see the development, especially in Europe, in the developing world, in the developed world, where you can see per capita CO2 emissions declining, and I would say rapidly declining. And obviously there's still room to improve, and obviously there's still a question of whether even the European targets will reach 1.5 degree or 1.7 degree, and if we're fast enough to deliver to 2045 or 2050. But I would like to shift your focus on the right side of the slide. I would say a lot of the discussion is not so much focused on Europe as it should be, and there's still a lot going on in the rest of the world. Which brings me back to the question of what is it that we have to do, and what is it why I still think that it's not too late, and there's a reason to believe that Europe can be in the forefront of this development, basically even serving as an example of how to do it. And I think especially Germany, which has I would say we've taken a very peculiar way of doing energy transition. Most countries that want to go carbon neutral right now are either looking at a lot of nuclear, a lot of hydropower, or very, very well-suited regions for wind and PV. And Germany basically has none of those options. We do have PV and wind installations, but from point of efficiency, those are usually less efficient than some of the most prestigious regions in the world, like Australia, for example, has very, very interesting regions for wind onshore, which has a percentage or efficiency rate similar to what we see only in the North Sea. And so this brings me to my last aspect regarding the carbon question, and this is the reason why I'm so glad to talk to economists today. And I think the most important questions regarding our future grid development and our customer base is the question of how to implement some form of, I would say, safety mechanism, which basically prevents the total loss of an industry base in Europe. When we discussed with BASF or Bayer or Thyssen, for that example, about their future prospects, maybe 3, 4, 5 years ago, when carbon prices were still fairly low, they were basically always looking at how long can we stay in Germany, how long does it make sense to produce here versus somewhere else in the world. And due to the, I think, due to the discussion of the cross-border carbon border adjustment mechanisms, this has changed. Those companies now actually see a possibility for an economical way of producing carbon neutral in Europe. And this is basically what is interesting for us as an infrastructure provider, because now we are facing actual demands in terms of green hydrogen, green electricity, all kinds of green fuels. I'm not entirely sure how many fuels we will see in the future. We've always had a diverse and heterogeneous set of fuels. We've never had a single fuel society, and I think all the talk about an all-electric world are still over the top. I think in the end we will see different fuels used simultaneously. But how to actually prevent this, how to actually implement this, and how to actually make sure that every single piece of product imported into a climate neutral European economy has to be a very challenging idea. I've worked on the topic of life cycle assessments, Ökobilanzen, for quite some time, and I can just say myself, this is a very difficult business, and it's not very precise in some regards, because it's determining on so many factors which are changing all the times. Like, for example, the emissions from electricity production in China or India, and all those factors have to be obviously evaluated almost in real time regarding such a carbon border adjustment, at least if you want to make it fair and predictable. Leaving that behind, I would turn your attention to the topic of hydrogen. Why is it that we're looking at hydrogen at the moment? And I've just tried to give you an idea of how much has changed in the business of transmission grid operators just over the last few months, actually. I think it was obviously in part due to the Bundesverfassungsgericht, which the highest German court actually decided that climate neutrality is a privilege that has to be provided for future generations. And this led to complete rethinking, or let's say at least a further acceleration of processes. And on the left side of the slide, you can see basically what we have been discussing since 2012. 2012, we started the process of national grid development plans, the so-called 10-year development plans we are looking at in Germany. First focused on 2022. We then did, at the beginning, we did a yearly update and looked at 23, 24, 25. And after that, we changed the rhythm of the grid development planning. And so now we're doing a bi-annually, we're doing it every 2 years, which means that we have some degree of freedom on whether to look at on what target year. And over the last few years, we have focused work on 2030 and 2035. We have done one extension for 2040 in the last grid development plan. And all those figures you can see down here basically represent what was the common census, the consensus opinion, the common sense of the regulator, the politicians in Berlin, as well as the TSOs and the energy supply side. And as you can see by the new numbers that are now currently being discussed and being analyzed and modeled, there's a huge gap. Maybe some of you are aware of I think the International Energy Agency usually produces charts where they predict the amount of wind and PV installations coming up over the next few years, and those charts look somewhat similar because they always underestimate those progresses. And well, basically this is the same thing we did in Germany. We thought that 120 gigawatts of PV installation were an ambitious target, and looking at how much we have done over the last few years especially, those were ambitious targets. We had a couple of years where we were only adding 1 or 2 gigawatts of wind per year, and not much more on the PV side. And now all of a sudden we are now talking about very mainstream ideas in Berlin of almost 400 gigawatts of PV installations, where we're talking very reasonably about 150 gigawatts of wind onshore. We're now talking about something like 65, maybe 70 gigawatts of offshore, which would basically mean the usage of the entire German part of the North Sea, which just to give you an idea, you would basically just keep free some small passageways for shipping. You would obviously try to keep some room from the coast, but otherwise most of the area in the North Sea will then be covered in wind parks and wind turbines. And just to give you an idea, on the lower right side hand, there's two questions from a technical point of view, which is most interesting to us. Obviously, the question of the potential, the theoretical, the economical potential overall, but also, and this is somehow forgotten, at least in political discussions, I think sometimes, is the gradient, or the speed in which those processes can actually unfold. And looking at those processes in those scenarios, we would then see some years with up to 18,000 megawatts of installed PV capacity per year. And just to give you an idea, the best we have done so far, beginning of 2010, 2011, I think, were about 6,000 megawatts. And that was a time where basically every technician you could find in Germany was climbing on a roof to install cheap Chinese PV. And now we're looking at a time where we probably have to triple that number. And again, starting from a very low point. So I think the next few years are crucial, because if we don't convince the public that this is actually feasible and that we can actually ramp up the speed of change over the next, let's say, 3 or 4 years, things start to turn sour, because they become increasingly difficult to achieve. And if you imagine just 2 or 3 lost years in for example, wind production, we've seen 1,000 or 1.5 gigawatts of wind installation last year, I think. 2 or 3 more of those years, and you can see that for the last few years, this just triggers an exponential reaction, which basically becomes, I think, unfeasible. And in the middle of all this is a small number I like to reference, and which is the capacity of hydrogen power to gas installations, power to hydrogen, power to methane, power to X, all kinds of possibilities are being discussed right now. And the number of 60 gigawatts is also, I think, very ambitious, and has to be discussed from a technical point of view, has to be discussed from an economical point of view, has to be looked at from an efficiency point of view. What is the most efficient way to give you some kind of other fuel beside electricity? And why is it that this hydrogen topic is so interesting to us? Well, it's basically, to sum it up in one picture, it's that picture. And these are figures that I actually got from our from our people in Brauweiler, which are looking at the grid 24/7, and they just provided me with some figures, and just to give you an idea about the volatility of the system we're currently already dealing with. We have last year we have crossed the installed renewable capacity in Germany of 100 gigawatts. So the system is already basically mostly renewable system from a point of installed capacity. It's not yet there from a point of produced electricity, because obviously there's this vast range of available power in field. And so what we're seeing is there is still times, even in 2020, where there's less than 1% of the installed capacity actually available. And so we will have to look at every possible solution. Basically, we will have to look at storage, and hydrogen comes into play as soon as you're not in the, let's say, intraday area. Intraday batteries and car batteries and all those kinds of storages will probably help a lot. But as soon as you're looking at seasonal changes and looking at the question of how to bring something like 100 or 200 terawatt hours of energy from the summer period to the winter period, the battery is no longer an option. And then you are looking, as of now, at hydrogen as the most promising candidate. But everything else, demand side management, is also coming into play, as well as maybe some remaining peak power plants, obviously carbon neutral peak power plants. I don't want to go into detail on that, because this is obvious to all of you. Obviously, we're looking at significant parts of the year where the electricity production is simply much higher, at least to what we are used on the demand side. And this brings us to another question, because one of the most interesting questions from my point of view as an infrastructure provider is, again, what is the let's say the operational range of this energy system going to be? And what you can see here on the left side is there's a very small range actually that we have operated the system in for, let's say, almost 50 years. The entire demand, the entire electricity demand in Germany has always stayed between more or less 50 and 100 gigawatts over this entire time. This is why we're talking about base load still with all that volatility going on. We still know that we have never seen hours where the load was, the demand was less than 50 gigawatts, basically. And on the other hand, we haven't seen much more than 90 or 100 gigawatts of demand. And those were usually peaks during very cold winter times due to a lot of heating with electricity. And the big question for maybe a few years back, the big question was always, what are we going to do in those times where there is no renewables? What are we doing basically to the lower end of this? What is happening if there is a demand of maybe 50, 60, 70, 80 gigawatts, and there's a very, very low number of renewables online? And for maybe a year or two, our focus has more and more shifted to the other side as well, because the question of what are we going to do with 200, 250, or even more, if you look back at the numbers from the slide before, maybe we have a system with 500 gigawatts installed renewables, which will mean 300 to 400 feeding in at the same time, very, very continuously for thousands of hours per year, probably. And what does that mean for the demand? Is there enough flexibility to go up to 150 or maybe even 200 gigawatts of demand? And what does that mean for transmission and especially distribution grids? So in the end, what I'm trying to tell you here is hydrogen might be possibly the most important solution. It's definitely not the only one. And so since we're not smarter than anybody else involved in this discussion, we tried to do a little crowdsourcing. And this is actually why the presentation is called System Vision. We started a project a few months back, where as part of our grid development plan, or preparations for the grid development plan, we started discussions with more than about 24 NGOs, customers, stakeholders, politicians, ranging from Volkswagen to Trimet, producer of aluminum, to Frankfurt Airport, to Germanwatch, Deutsche Umwelthilfe. There were discussions with Greenpeace and the UND and all kinds of stakeholders. And we all asked them to basically characterize, parameterize their future vision of a climate neutral German and European energy system. And we've come up with very interesting results so far. And I'm not able to share all those results yet, because we're still in the works, and this will be published over the course of the next 2 months. And I'll just tell you to keep tuned in, stay tuned and look up on the website or our Twitter feed what is happening with that. But just to give you an idea, what we're basically doing is, first and foremost, is a simple energy system model. But for the first time, we're basically doing this as an integrated, holistic view, a cross-sector analysis where we have a electricity grid, methane grid, as well as a hydrogen grid possibility, at least. And we're using a combination of optimization processes and some linear models, which are basically there to give us a first idea of how feasible those different scenarios are. And we will then look at what does that mean in terms of imports and exports. What does that mean in terms of sufficiency of already existing infrastructure, and so on. And just to give you a clearer picture, all of those parameters, we're usually doing a calculation for 8,760 hours per year. And we are always doing this on a regionalization where we're looking at every single grid connection point from the transmission side of things. So but Germany is basically cut down into, I would say, 200 little pieces, more or less. And what you can see, what the colleagues try to show in a very graphic way, is basically the future imbalance that we're facing is like nothing we've ever seen before. The average transport distance of a single kilowatt hour, or a single electron, if you want, has been fairly short. We had a very homogeneous distribution of power capacity over Germany, with a lot of nuclear, obviously, in the southern part of Germany, even coal-fired plants along the Rhine River, Karlsruhe, Mannheim. There's still hard coal power plants online. They're now coming offline as we're speaking. But you can see the distribution, even looking at 2022, that was fairly evenly distributed. And what we're now looking at 45, even though there's a lot of decentralization happening, even though there's a lot of PV being installed on rooftops, we are still, from a grid point of view, we're still facing this enormous infeed of offshore wind, which is a very centralized and, to be frank, even a very far away form of energy. And if you want to include that, and I think from every simulation we've seen, from every model we've seen, we do need to include this, because it is probably not feasible to provide for the entire industry that I just talked about, the chemical industry, steel industry, and so on, just with PV installation. So we will need those amounts of electricity produced by offshore wind. And now I've promised to give you an update on what the last molecule is. The secret is it's polyethylene, specifically cross-linked polyethylene. And why that? Well, basically, what I'm trying to tell you is, we do see as one solution regarding all those congestions that we are facing, technological advances that we have seen over the last few years, especially regarding cables. You can see in the right half of the slide a picture of a 525 kV HVDC cable. That still says prototype. By now, it's actually passed all the tests required. And we are currently installing those cables on land as well as on the sea. Basically, every single offshore connection that is coming online, I think, beginning in 3 or 4 years, we're currently using a smaller version of that cable with something like 320 kV. But the newer cables are coming online. They're being bought right now. They're being planned right now. They're being discussed right now because they actually change a few ecological properties. We have a lot of discussions regarding warming of, for example, the sea, the sea floor. How much is it possible to have an increase in temperature around those cables? Just to give you an idea, a single cable like that, or 2 cables combined, can transport something like 2,000 megawatts. So basically the equivalent of 2 huge nuclear or coal-fired plants. And this is why we still believe that transmission grid expansion is one of the tools that we need in our toolbox. And this is why we still believe that it is possible to actually achieve a lot of all those targets that I've introduced and have shown to you. To just give you an idea what it would cost to not do that, we've done some calculations here where we basically put the targets for 2040. This is not even 2045, I think. Those are the 2040 targets put on the existing grid infrastructure. And putting that on the existing grid infrastructure would then lead to redispatching costs of about 6 billion euros a year, which means there's not much free market left, basically, because the market doesn't function due to the physical congestions that we're facing basically on a daily basis by then. On the current side, we've reached 1 billion in redispatching costs over the last few years, and we've always tried to reduce that, obviously, and some grid connections have come online over the last few years, which have helped reducing those costs. But the perspective of such a massive increase in redispatching costs and even redispatching, how do you say, it just doesn't make any sense to keep up the market designed in the way it is right now if you are not able to have a physical backbone that is actually able to transport all that energy, right? And so this is what we are doing. But just to give you an idea of how large the toolbox is from my point of view, grid expansion is obviously in there. But first and foremost, what we always try to do is better usage of existing grids. And there I just want to mention the topic of thermal rating. We started to equip more and more of our overhead lines with equipment that measures the wind speed, so that we are able to see how much cooling our high voltage lines are actually getting from the wind. And if the line is cooled properly, we can then use it to transport more power, which is basically the idea of thermal rating. In the past, we've set let's say a certain rating which allowed us to transport 1,000 or 2,000 megawatts over line, and that was kept as a constant because we didn't know a lot about the environmental factors around the line. We didn't simply have the information, and we didn't have the strategy or the digital equipment to work with that. And this has changed obviously over the last few years, and now we are having a lot of real-time information regarding all our lines and regarding temperature along those lines, and now we can use the existing grid much more efficiently. And there's still room to improve, obviously, and we're talking about all of that right now. But we have also started discussion with the Ministry of Economics regarding the implementation of new peak generation capacity. We have just last week offered a presentation where we were thinking about system services, for example, like short circuit power, reactive power, frequency reserves, and so on. And there's a lot of things changing right now. All of those system services will be required in the future, and they have been provided for mostly by the large power plants of the last decades. And now that those large power plants are going offline, we have to look for some kind of replacement. And I think renewables will be able to provide a lot of those system services, but not all. Every inverter-based technology has some limitations, especially if you're looking at things like short circuit power. Short circuit power is always in demand if you have a very inverter-based an energy system. And so what we're doing here is even from a technological point of view, we do not have all the answers right now, and the next 20-25 years will be very interesting even from a technological point of view. There's a few more no regret measures or very reasonable things to do, like increase of import and export capacity, which we are currently working on. Amprion has just finished the first electricity connection between Belgium and Germany. We never had one over the last 50 years. That simply wasn't needed. We have installed a DC cable between Aachen and Liège, Lüttich. That cable has been planned and built in about 4.5 years. So it is possible to build grids. You always read about those very long times it takes for the very long lines, like 10 or 15 years for some of them. But if you have a shorter project, if you have a good understanding with the government officials that are responsible for the planning, and if you're talking with the people that are actually affected, you can see a significant increase in the speed of how you can build those projects. Yeah, and again, last but not least, again, I see the significant use of power to gas and hydrogen as one key factor regarding the question of how do we most efficiently use the sources available, and how do we find a way to optimize our infrastructure needs. I have two more small subjects I want to just very briefly address, and maybe we can deepen the understanding in the discussion. And first of all, if we come to the point where we will actually use all the tools in the toolbox, and when we're actually able to implement an energy system with all those 400 gigawatts of renewables, there are still questions to be answered. And one of them has to do with system security. I mentioned some of those system services, but the list is not complete. There's some things that we're just now starting to look at. Momentary reserve is one of them. Momentary reserve is basically a function or a capability of the grid to withstand large failure situations, loss of a large plant or an offshore wind park, or loss of a line, which would then lead to hopefully a situation where we can handle that single loss. The entire grid structure is usually operated in what we call a N-1 mode. So we have to be able to withstand the loss of every single piece of equipment we have, from a transformer to a line to a plant. Everything has to be exchangeable. But in a future scenario where there is a very different set of installed capacity, where there's a very different set of rotating masses, for example, we might end up in situations where even the loss of a single piece of equipment can lead to a cascading error, which then leads in the end maybe even to a brownout or blackout situation. And this is what our experts are thinking about most of the time. As I mentioned in the beginning, this grid has not seen a complete black start, a restart of the entire system, maybe ever, for at least not for the last 70 years. And so every single failure we have seen over the last decades have always been associated with smaller losses of load. We have lost Italy once or twice. We've had system splits that resulted in load shedding, for example, dropping Paris or Cologne from the grid, but we were always able to then capture the system and restart it from a point where it was not completely down to zero. And this is the big difference looking in the future, where we might not even have the capability to restart completely. Obviously, restarting demands some form of energy that I'm able to control. And if we're just looking at PV installations, which might not be available during the night, or wind installations, which might not be available when there's no wind, we might end up in a situation where we have a system running that we can't restart if it actually fails. And so this is something that we have to look at, and this is something that we're calculating. And just to give you an idea, just a small figure, the area of about 50,000 square kilometers, which is basically the entirety of the southern German region, will by 2030 will probably have no or almost no rotating masses through synchronous machines. And synchronous machines, which are the big generators in the remaining power plants, they have a few technical advantages, to say the least. And so this is a very interesting question, even from a technical point of view. How do we implement that in an inverter, and what are we able to exchange them with? And the other side, I think, is probably coming back more to your field of expertise for the economists. The distribution between capital and operational expenditures is changing rapidly as well. And so what we're looking at is a system where probably by the mid of the century, something like 80 or 90% are capital expenditures, because almost all renewables are just capex. All of our grid infrastructure is just capex. Most of the storage equipment is just capex. You have obviously you always have some form of losses, which you can attribute to operational expenditures, but the vast majority of the costs of the system will be capital expenditures. And we are therefore very interested in all kinds of ideas of how are we going to finance this future system. Does it still make sense to charge people per kilowatt hour or megawatt hour if electricity is abundant for thousands of hours? And does it still make sense to strongly separate the costs of grid from the cost of the product itself? And so there's a lot of things going on right now. And if you're looking closely at what's happening, if you've read the election programs for all of the major German parties, they basically all want to reduce the renewable subsidies, leading to a co-financing, and this has already started, co-financing through the tax system, basically. And we now have a climate fund associated to the federal government, which allows us to put billions of euros each year into those mechanisms. And so the first idea of basically saying, well, we will have a system maybe mostly financed through taxes. We might even have to live with certain congestions, even especially looking at the distribution side of things, looking at electric vehicles, for example. How are you going to cover 30, 40 million of charging points in the distribution grid? That might lead to the big question of, are we going to work with prices? Will we allow people to pay for faster charging and so on? Or is this more or less a socialized problem where we say, well, there's certain congestions, and the let's say the secondary substation, the transformer at the end of the street decides what garage goes first and which garage goes last. And I have no idea what's happening right now, but there have been changes proposed to the way we charge for grid infrastructure that would lead to basically having to work with those congestions for a very long time. I'm not sure that we will provide everybody with a install capacity that they actually want to have. But again, I'm very interested on what you are thinking, and so I would end on that note. I'll show you again the website I referenced. If you want to look it up, it's unfortunately still only in German, and there's an English translation coming up over the next few days. systemvision2050.de. We have about a dozen partners online already. They present all their ideas and all their figures. If you want to see how much hydrogen are they importing, if you want to see where's the heat coming from, how much mobility, electricity demand are they seeing, you can all look it up on the website, and you can ask me anything you want. Thank you.
Well, thank you, Thomas, for this insightful and exciting talk, and all the views you shared with us. I hope people are not so stunned that they don't have any questions anymore. But well, as we said, please raise your hand or write something in the chat, so then we will promote you that you can ask your question. So I don't see anything if Mike is not saying so. I'll take the opportunity to ask the first question, or a first question. Many aspects of your talks of your talk sort of pointed out things that need to happen, and you also talked a little bit about implementation. I was actually wanting to ask you a question about the grid and the 10 years, but you answered that in going that is actually possible in Germany to have a grid expansion which is quicker than 10 years, and yeah, so that's nice to hear. But then maybe what are your views on an implementation of a cross-border carbon tax? So what do you think, which aspects should be covered? Because you mentioned that when you were talking with BASF and TriMet and these players here. So do you have any views on possible strategies of implementation of that?
I have to be very careful because it's such a large topic, and looking at global trade and all the implications that would have, it's obviously not my expertise. And from the infrastructure point of view, it's an interesting mechanism just to give some form of security and planning period for industry in Europe. And this is why we, as a company, we find this a very interesting idea. The devil is in the details, obviously. This is why I mentioned the life cycle assessment. If you're looking at every single, I don't know, kilowatt hour of imported hydrogen, if you're looking at every piece of plastic that's coming from China, and you have to answer the question of how much carbon is that actually carrying, that becomes very tedious, very difficult, very fast. And in my worst nightmares, worst case nightmares. I'm seeing a huge government portion just being staffed with thousands of people, which are basically not doing anything else than life cycle assessments. I don't know if that is the most reasonable way. Obviously, all the ideas of climate clubs and getting other countries to join and having a worldwide kind of ETS system are probably more interesting. Maybe the carbon border adjustment is just the boogeyman in the room, which brings other people to the table so that we can actually find a more sensible solution. But this is why I showed the China slide. It's basically I'm not a friend of saying we don't have to do anything because Germany is just 2% and we can't change the world. That I'm very much of the other opinion. We have to do something. We can do something. We should show how it could be done. But still, there's a question. I mentioned the historical or ethical side of things, and so what we are looking at, even that has concrete technical implications for us, because we're now looking very intensely on the question of direct air capture. Will we stop at zero emissions in Europe, or due to our historical challenges or responsibilities, will we go on to net negative emissions? How do we arrange that? Is CCS the best way to do it, CCU, or how much? We're now, the discussion has changed over the last few months so rapidly. Now we were used to paying 10-15 euros per ton CO2. Now we're already facing 60. The scientific discussion has now brought up something like 180. There's the last time I checked, there was a publication saying 2,000 euros per ton. If you're going up into that region, direct air capture becomes very feasible very fast, because then it makes, from an economic point, from at least from what my people or my experts have been telling me, that might be a possibility. But direct air capture needs a lot of power again. And so it's like a catch-22. It might be even a solution of what to do with all those hours where we have electricity abundantly and don't know what to do with it. Are we going to make hydrogen with it? And that hydrogen, obviously, if depending on how you use it, I mean, we now have people proposing to burn hydrogen in a CCGT turbine, which I think is not a very reasonable idea. I have something as valuable as hydrogen, and I should use it in a fuel cell or in the industry processes. I can't substitute otherwise. And so, yeah, again, I'm maybe slightly changing the subject because everything is connected with everything, I think. But yeah, we would get some clarity from a cross carbon border adjustment, I think, because that would just give the industry a perspective of how a carbon neutral economical space would actually work. And I think that has changed minds, at least with the industry partners that we are talking with.
Right. Yeah, thank you. We had this topic in the first keynote as well, where Simon Dietz was talking about disclosure of carbon footprints of corporations, and not a lot is going on. So that's precisely what you were saying. So to find really out
sorry for interrupting. Maybe the biggest force on that is the finance side of things, because that is at least the pressure that we are seeing right now. As a TSO, I would say something like 90% of our carbon footprint is coming from losses. Mm-hmm. And as you know, our business, I said it in the beginning, we are investing something like 24 billion over the next 10 years, and about 2/3 of that is how do you say, Fremdkapital. It's not our own money. We have to go to the market, right? And we have to get bonds and things. And the main question being asked right now on the capital markets is the question of sustainability. So it's Moody's and Fitch first, and then you have to go for your sustainability grading. And even in the amount of money we are asking, this can make up to 0.5 percentage point of difference, whether you have a green financing or a classic financing. And so there's a lot of pressure coming, at least to, let's say, the private enterprises. I don't know if this really affects the governmental players, like the big oil companies, or which at least half of them are still state owned. They're going to refinance everything with 0% anyways right now. So yeah, that is a very important aspect, I think.
Yeah, there's a lot of scientific research going on precisely on that question, and the evidence is that you see extra charges if you're a brown company and not a green one.
Yeah.
So that's one of our research areas. Well, I see one question in the chat, so I'm going to allow that, although we are almost running out of time. But sorry that I asked first, but I was interested. I read that to you. It's from Runtiang Feng. As far as I understood, we may reach a system with 400 gigawatts installed capacity while the demand stays around 100 gigawatt or won't reach 200 gigawatts. Does it mean we have more than double capacity to fulfill demand? It is clean in terms of emission and secure in terms of fluctuation in renewables, but how efficient it is?
Yeah, that's a very, very important question, I think. Well, from an economist's point of view, you would always say, well, if I have to curtail, if I have to throw away some of that power, that might be okay if the overall, let's say, efficiency is okay from a economic point of view. What we are seeing is that people are not very happy with current curtailed wind power. This is actually becoming a question of acceptance as well. And I personally believe that we will not be curtailing wind power significantly, and we will not be throwing away that energy. So the question that we are asking is basically, what are we going to do with it? Are we going to store it near the place of production? There are ideas of, for example, hydrogen power to gas modules on offshore platforms, so that you're taking in the wind offshore and already producing your hydrogen on the sea, so that you could store it there or bring it to the coast by ship, so that you had some kind of buffer, some kind of flexibility already provided at the point of generation. And what I showed you was the demand side, basically from our grid perspective again. If I have a grid side demand of 100 or 150 or 200, I have to provide that instantaneously. So the question is it's a space-time mixed question, right? It has spatial as well as time aspects, and the grid side of thing is one possible solution. And I think we might see higher peak loads, but so far I have not seen a study that answers perfectly the question of what is the optimal peak load for the German or European system. And so everybody's just we're always just assuming that it stays more or less in the same bandwidth. From an economical point of view, it might be more reasonable to actually increase that significantly and give the energy use side more flexibility. I'll give you one short example. We talked to BASF and we basically asked them, if you could choose between 2,000 megawatts of electricity connection or 2,000 megawatts of hydrogen connection, what would you take? And their simple answer is, we would take both, because we want to have the flexibility. And from an economic point of view, that might even be reasonable. The question is, where is the highest amount of wealth created with that energy? How much of that efficiency are we going to use to minimize or optimize the infrastructure side? But the infrastructure is always just a way to means, right? I mean, the infrastructure is just there to help someone else do something with energy. We're not using the energy ourselves. And so if someone like BASF says, we want to have flexibility, we want to be able to exchange hydrogen for electricity depending on prices, depending on our needs, depending on production processes, that from an economic, from a national or even European point of view, might be a very interesting idea to say, okay, we need some form of, let's say, from an infrastructure side, like an oversized infrastructure. It's not optimized or minimized. The infrastructure is maybe larger in order to give more flexibility to producers and end users. And yeah, I haven't seen a lot of work being done on that, because it's such a technical and economic question, integrated in and as I said, we would be very open for cooperations on that question, because obviously that makes a lot of difference in the way we plan our grids.
Well, thank you, Thomas. So thank you for the talk and all the questions. I'm sorry that we have to stop now. If we had a physical conference, everybody would now rush out of the room to the other room, but we have 3 minutes to change our virtual sort of setup. So thank you again for being with us. Thank you for sharing your insights. It was very, very nice explanations of things that are currently happening, and we really very grateful for this excellent talk. So thank you again. Thank you. And now, yeah, people run to the other room.
Hope to see you soon.
Thank you. Bye.